In 7.4, we're going to be working through the addition and complement rules with probability. In this video, we're first going to focus on the addition rule. So to start this, we are going to need to set up an experiment here and some different events from that experiment. In this video, we're going to do all of our examples with a deck of cards. So our experiment is to draw one card from the deck. The first thing that we need to figure out with this is how many cards are there in our standard deck of cards. Well, we have a picture over here on the right of our deck of cards. The deck of cards consists of 4 different suits, and each of the suits have 13 cards, the ace through king. So to figure out our number of cards in the deck, we can take 4 and multiply that by 13 to give us 52 cards in our entire deck. This is the number of elements in our sample space because we are only drawing one card from the deck. So n of s is equal to 52. So now let's set up some different events with this. We're first going to have A be the event that a heart is drawn. So we take a look at our deck of cards and we grab all of the hearts and put that into this event A. So that is our 13 hearts. So now to find our probability of A, well, that's simply just the number of things in A divided by the number of things in our sample space. So this gives us 13 over 52, which then we could simplify that to be 1 over 4. The next event that I want here is event B, and we're going to say that that is a face card is drawn. I'm not going to write all of these cards out for what they are. Instead, I have a picture over here on the right side of all of our face cards from the deck. That's our 4 jacks, 4 queens, and 4 kings. So now to find our probability of B, this is the number of things, number of elements in B, divided by the number of elements in our sample space. So now, how many different cards do I have in event B? Well, I can count that up over on the right. We have 12 different cards there out of the 52 cards in the deck. And now we could simplify this fraction. I'm going to skip that for now, but you could simplify that, reduce it to its lowest terms. But the question that I want to ask here is, do some of these cards satisfy both conditions of being a heart and a face card? And yeah, if I take a look at my 2 pictures over here on the right side, if I look at my picture of all the hearts, the top picture, I can see that there's 3 face cards in there. And if I also take a look at the picture of the face cards, we can see that there are 3 hearts in that picture. So yes, there are some cards that satisfy both. And now the next event that I want to set up here, the last one, is what I'm going to call event C. And this is going to be a black 2, a black 3, or a black 4 is drawn. And that's these 6 cards over here on the right. We have 2 different 2s, 2 3s, and 2 4s in the set because half our deck is red and half the deck is black. So now our probability of event C happening, well, the number of elements in C over the number of elements in our sample space. There are 6 different cards in this event out of the 52 cards in the deck. So now that's our setup for the 3 events we're going to use for the problems on the next page. So I want to start with a definition here. We want to go over mutually exclusive events, and we call this as being two events are mutually exclusive if they cannot happen at the same time. Essentially meaning that they do not share any elements. They don't have any overlap, so there is nothing that they share between the two events. So let's think about our two events B and C from the last page. B was the face cards, and C was the black 2, black 3, or black 4. And now I want to know, do they share any cards in common? Are there any cards that they share? And the answer to that is no, because event B is face cards. Those are jacks, queens, and kings. And event C are the black 2s, 3s, and 4s. There's absolutely no cards that they could possibly share for that. This means that those two events, B and C, are mutually exclusive events. However, our events A and B from the last page, A is our hearts and B is the face cards, those are not mutually exclusive because they share cards. We saw that they shared cards. There was 3 that they shared, so they're not mutually exclusive. Okay, so now we can start to work with our addition of probabilities here, and the first one that we're going to do is specifically for mutually exclusive events. So if we have 2 events that I'm just calling A and B here for the terms, and they are mutually exclusive, they do not have any cards in common, or any elements in common, I should say, then the probability of A or B happening is simply just the probability of A plus the probability of B. So we can just take the 2 probabilities and add them together. We can only do this when there are no overlap between the 2 sets. So if we think back to events B and C on the last page, B as our face cards, C as the 2, 3s, and 4s that are black. I first want to know, what is the probability of B and C happening? Well, the and is the intersection of the 2 events. I specifically want B and C to happen at the same time. Well, our intersection is 0 cards out of the 52, which is just 0. It's impossible. We can't draw a face card and a black 2, 3, or 4 at the same time in that one card that we get. But now our probability of B or C happening, well, since they don't share any cards, we can say that this is equal to probability of B plus the probability of C, which we already calculated those. We have probability of B being 12 over 52, and the probability of C being 6 over 52. And now, when I have 2 fractions and I want to add them together, as long as the denominators are equal to each other, in this case I left them both as being 52, I can just add the numerators together and keep the denominator as 52. So this gives us 18 over 52 as being our probability of B or C happening. However, so next, not all of our events that we have are mutually exclusive. On our last page, events A and B are not mutually exclusive. They share cards. So with this, we need to make sure that we do not count the elements in both sets twice. This is because those events that they share, the elements that they share, are only in our sample space once. So on the last page, A and B shared the Jack, Queen, and King of Hearts, but those 3 cards are only in our deck one time. So in our probability, they need to only be counted once. So in order to calculate our probability of A or B for any event, or any 2 events that we have, we usually use this when they're not mutually exclusive. However, you could still use this if they're mutually exclusive as well. But it's simply just going to be our probability of A plus the probability of B minus the probability of A and B happening. So a little bit I want to spend here to go over the difference between and or. So the and statement here, probability of A and B, is telling us that they happens at the same time. So when we draw that one card, it needs to satisfy both of those 2 conditions within that one card that we get. While the or, so our probability of A or B that we're trying to calculate here, is either of the 2 conditions. So we're drawing one card, it needs to satisfy A, it needs to satisfy B, or it could do both if it wanted to. But it needs to just satisfy at least one of the 2 conditions that we have. So now, lastly, let's calculate our probability of getting a heart or a face card. Those are our events A and B from the last page. Well, we can use our formula here to figure this out. This is going to be our probability of getting a heart plus the probability of getting a face card minus the probability that you get both a heart and a face card in your one draw. So now our probability of getting a heart, well, we have 13 out of the 52 cards in our deck that are hearts, plus our probability of getting a face card. And we have 12 face cards out of the 52. And then we need to subtract those that were counted twice. The Jack, Queen, and Kings of Hearts are counted in both the 13 and the 12. So I need to subtract off one copy of that essentially. So we're subtracting off 3 out of 52. So now all of our denominators are the same, they're 52, so we can add and subtract the numerators. 13 plus 12 minus 3, and that gives us 22 out of the 52 cards in the deck. So now, lastly, what I'm going to do is go back up to our picture of the deck of cards to work through this sort of in a visual aspect, if that might help your understanding. So I am going to highlight our hearts here in the top row of our deck of cards. It's those 13 cards at the top. And then I'm also going to highlight our Jacks, Queens, and Kings, our face cards. That's on the right side as our event B. And now I want the probability of either of these two events happening. Well, we had the 13 hearts that I have at the top, and we have the 12 face cards. If we add those together to get 25, these Jack, Queen, and Kings that are highlighted both times are being double counted. But those 3 cards are only in this deck once. So we need to subtract off essentially the double amount that we did here. So that's where we get our 22. One thing that you could do when you're have the sample space like this, you could highlight all of the cards or all of the elements that are in either of these two, and just make sure that you only count them all up once. So if I were to do this, I highlighted all my cards, and now I just highlight how many things, or I count up how many cards are highlighted, and that will tell me the correct number as well.